132 is right.
Right?
No way.
No, you're supposed to.
Alright.
The reason
It
choice
could be.
So,
Because if you divide by negative f, then there should be.
Shouldn't be. Yeah.
always a good idea to draw a picture. I like to draw these before or initial
I'm gonna give the.
and final moments, before and after, or something like that. So I know typically in the past with kinematics, with like a free fall problem, right? The problem starts right after it leaves the hand and ends right before it hits the ground. But now we're dealing with, well, what about the motion of when that ball is thrown, right? From 0 to something, and then you let go and it's doing, whatever. So that's kind of what we're dealing with here. And if you notice, a lot of times when you use impulse momentum, it's happening really fast. So hence that idea of impulsive force, right? It's happening really fast. So the change in time is 0.045 seconds. I hate when they do like scientific notation for like next to no reason. Times 10 to the -2. Why? It's so much easier to write like that. But we got 132 newtons of force. The mass of the ball is this. Here's the initial moment. There's the final moment right there, and we don't know what the velocity is at the end. But you can always look at this as either an impulse momentum question or a conservation of momentum question. And I'm going to really elaborate on that next. But in this case, the data we're given, impulse and momentum is going to be the easiest way to look at this. So, because I'm giving F net, delta t, m, etc. So, but if you wanted to be a stickler with using that integral idea, the integral of F net dt equals the change in momentum, well, okay, the integral from some initial time to some final time, so that's 0 to 0.45 of, 0.045 of, what's F net? 132 dt. What's the integral of 132?
132.
So it's t, so it's going to be 132 times t, and I evaluate that from 0 to 0.045, and you get 132 times 0.045, which is something. What did you guys get?
5.94.
40.
5.94.
5.94.
No, just
5.94. And because it's momentum, even though we use impulse, if we're talking about impulse, we tend to use Newton seconds. If we're talking about momentum, we tend to use kilograms meters per second. They're the same units. We just use different ones when we're talking about different things. Technically, Newton seconds is fine, but yeah. Yes. Or you could have just went, well, those are average values, so I'm just going to multiply F net times delta t, right? So that's totally, yeah. I'm being, just to show you that either way would work. Yeah.
So on a test, it would be okay when you put Newton seconds?
It would be, but you're playing with my emotions, so yeah.
Okay.
I don't know. It's just it looks weird. It's the same way that impulse. Like I've talked about impulses. The symbol is J. That's like a recent thing, and it still weirds me out. Like I can't. Because one thing I'll mention this really briefly. So we've got basically these two ideas that what's that give you? That's work, right? That's work. And that equals the change in energy, right? So if you integrate a force with respect to position, you get the change in energy. But if you integrate a force with respect to time, that's the change in momentum. And these are like the two big ideas in mechanics to a physicist. A physicist always looks at a problem, and one of the first questions they will ask themselves is, should I go at this with a work energy approach, or should I go at this with an impulse momentum approach? Most of the time, one of it's easier. One of the ways are easier. Energy is not always the easiest way to look at it. Momentum is not always the easiest way to look at it, but often it's easier to, yeah. But you can kind of see, right? very similar forms, yes? Yeah, because it's just two different ways of looking at it. One of them is with respect to time, and it turns out momentum is that quantity right there. One of them is with respect to position, and you get that quantity right there. With work, you take the dot product, so you get a scalar out of that. With force, you're just multiplying it by a scalar quantity, so it scales up or down, and that's what the change in momentum is. Sorry, had to bring that up. Because it kind of summarizes everything quite nicely. Okay, for part B, it then asks us to find out the velocity. How fast is this thing going at the end? I'm gonna, let's see, I'm gonna extrapolate from here, and I'm just gonna go to F net delta t. I know you could use your answer from before, but I want to show kind of how this works. Equals the change in momentum. Well, that's the final momentum minus, I'll call it mv2 minus mv1. Or did I call it 0?
No.
Did I call it 1? Okay. Yeah, well, yes. V1 is equal to 0. So all this is just going to be 0. So that's going to give me F net delta t, and I can divide by the mass, and that'll give me V2. What does that end up being? 42.4?
Yeah.
Or even 42? So something like that.
Yep.
Yeah. So, but yes, you could use, I mean, this is the change in momentum. That's the change in momentum, so you could have used that answer to solve for it. Either way works. Okay, but then the ball reaches the batter.
Oh.
I know, right? That's what the other period said too. Well, we know V2 now, because V2 is what the approach is, so that's 42 point, what was it again, 4? Oh, the mass again was 0.14 kilograms. 1.4? Or 0.14?
Yeah.
1.4?
Yeah, 1.4.
So yeah, and they give me that the net force is 1150 newtons. The time is 9 times 10 to the negative 3, and the mass there, and it asks us to find out what's the speed here, right? How fast is it going there? Again, I could go, oh, should I use impulse momentum or work energy or conservation of momentum? Impulse momentum is going to be the easier way to look at this. So they are all average values, so I'll solve this one kind of more using F net delta t is equal to my change in momentum, so that's my final momentum minus my initial momentum. Sorry, I'll say 2 to 1. Wait, 3 to 2, right? Yeah. And so, okay, I got my impulse, so that's F net delta t. I'm isolating V3, so I'll add MV2 to both sides. MV2 equals, divide by M, so divide by M, that's going to be V3. Yeah?
Yeah.
Okay. And then, bringing all this over here, so it's going to be F net. Now, this is why it's important to draw a diagram. Which way is my impulse pointing? Yeah, the bat is exerting a force that way. Right? Does momentum care about direction?
Yeah.
It does. So this is negative 1150. Now, yes, if you change the direction of your diagram, that would change things. So, okay, times the time, that's going to be 9 times 10 to the negative 3, plus the mass, which is 0.14, times the velocity, which is 42.244, divided by the mass, 0.14.
Oh, I think I know why. It's because you made the negative.
So what does V3 equal then?
Oh, wait. Never mind. You get it.
Negative 116.
Oh, wait. I'm not using
Wait,
conservative.
it's negative 31.
It's negative 31.
30 something.
31.
Negative 31 points.
Time out. I got 116.
I got 116. Hold up.
I got one. I also know.
Okay, I did it completely wrong. First time.
Wait, so you can just do negative?
I don't throw in the negative. It is negative because it's pointing in that direction.
Oh. Where's the up?
So let's. All right. Let's. So net force is
knew
negative.
it.
Correct. So the impulse
I
is
knew
negative.
it.
Now, if you have the ball going this way, which way? So what would the velocity be? Negative. So the momentum would be negative. But then the bat hitting the ball would point which way? Positive. So either way, you're going to be taking the difference of these two things. It depends on how you visualize the problem. Some people last period they did the opposite. They had the ball thrown this way, and then the bat hitting back that way. You'll get the same answer, right? Wow. In my version, I'm pointing in the negative direction, but it's pointing away basically from the batter at the end, right?
Why is 11 negative?
And if you do it even with the batter, if you do it with the batter being this way, again, the ball points in the direction opposite the batter, which is the same answer.
Yes.
That's why I chose this problem, is because of that moment right there. Yeah.
Why can't left?
I know, right?
We can't. But why is it?
There's a method to my madness. So, questions there? Because now's the time to ask. All right. Exam tomorrow. So, and then lastly, this was just a fun one. What is the force that the ball exerts on the bat?
I didn't get it.
What part was that?
1150 because of Newton's third law.
Darn straight! Yeah!
Okay, good.
It was that simple.
Right?
Good.
Yes. If the bat is exerting a force on the ball, right, of negative 1150 newtons, then the ball is exerting a force on the bat of positive 1150 newtons, right? It's the whole reason. Anybody ever hit a baseball before? Or a softball or anything?
That's why I go like.
Exactly! You go, ah!
It does
Jeez!
sting your head.
Baseball is, yeah, exactly! Ah! That's the force from that baseball exerting back on you. Questions, comments, concerns there? So yes, third law still applies. Woo! I know, right? All right, we got it.
Yeah.
We're gonna slowly go back to your guys' lab. So hopefully this is similar to your guys' lab. You remember here's a collision that's taking place. In case you've forgotten.
Let's go.
Two cards.
So here was. Whoa! How did that change? I didn't change anything else.
Oh, the other green one.
The more I do this,
Why is it It's like London London News sponsor.
Oh, now it's going.
Mr. Forney just proved the world's not
That's why they're.
It's a cooking string.
Because if the earth was round, it'd just be like going off.
Alright, so yeah, basically the collision is taking place here. Again, we got a before and after, so there is a collision taking place. So it's basically this. I'm not showing the collision because there's only so many diagrams you can draw. So yes, you got before and after the collision, but in between there's a collision of some sort. So before, boom, hit, and there you go. So they're both moving at the end to the right, and that's kind of like I think the second one that you guys did right there. So we got this card going into this card, and what I want to do is show that you can always use impulse momentum. You can always use conservation momentum. It's again your choice. You get to choose. I know, right? This is America. Yeah. All right? Freedom. Choice. You get to choose. You don't get some government bureaucrat telling you what to do. So,
No, 2020.
So I'm going to choose, now, in your guys' lab, what did you choose to be the system or object? Whether you knew it or not. The entire thing, right? You said all of this is my system. That's what I care about, right? And then you calculated the momentums in that system and you found out it was a conserved quantity. We're going to look at this the opposite direction from what you guys did in your lab. We're going to go from impulse momentum and see that of how the conservation of momentum goes. So I'm going to start though by just saying object 2 is my object. That's the thing I care about, right? And that's it. So when I look at this from before the collision to after the collision, is there an external net force or a net impulse acting on this? Yes. From what? What causes that? The other block is now this external force acting on my system, right? So in that case, I go to then, all right, well, the integral of f net dt equals the change in momentum of my system. All right, and so let's see, the integral of the force dt is equal to mv final minus mv initial, and I can solve things that way. So if I could, like you guys did when you collided your carts into the wall, right, you got impulse data. So if you get impulse data or force data or time data or something like that, and you got you can use this to solve for things, right? But often now, unless you have a fancy schmancy lab quest like we got, right? I mean, back in the day, they didn't have that kind of thing. You had to, I mean, yeah. Or, you know, you're stranded on a desert island, you want to find out what something's mass is. But yeah, I mean, you know, so oftentimes though, we use, so you can solve like this. That's one way to look at this problem. So I got this, and there's an external force that's going to change the momentum of my object. At first, my object's momentum was 0. An external force showed up and changed the momentum to something different. Yeah? Okay. Next up, I'm going to use the same situation, but now I'm going to choose, like you guys did in your lab, everything is my object. Or my system. What I do?
So your starting point and end point was like perfect. Wow. Like you can't, you don't know where you started.
Anyway, so if everything is in my system, are there any external net forces acting on my system? No. Are there forces acting on my system?
Yes.
Yes, such as what? Gravity's acting on it. Normal force. But they add up and cancel. We're going to ignore friction. But they cancel out. Right? They cancel out, and now I got no external forces acting on my system. So you could, if you did not know the conservation of momentum, you would go, oh, all right, let's see. Integral external net force, dt, equals the change in momentum of my system, mv final, that'd be the change in momentum. But the external net force is what? 0. So all this goes away, and you would absent-mindedly, because this is then the sum of the final momentum, right? It'd be the total momentum of object 1 and object 2 minus the sum of the initial momentum, the total momentum of object 1 and object 2 at the beginning. Well, and then you go, oh, I could add that to the other side, get rid of that negative there, and this would be that the initial momentum, the sum of the initial momentums equals the sum of the final momentums, and lo and behold, you showed up at conservation of momentum.
Yeah.
Yeah. So something that you guys found experimentally in your data shows up in the basically that impulse momentum theory or law or whatever you want to call it. Yeah, conservation of momentum. So the total. So now this is whatever's inside your system, whatever you choose. You got two objects. You got two objects. So this would be we could write this as, well, it's momentum 1 plus momentum 2, and that's basically just going to be m1 v1 initial plus m2 v2 initial equals m1 v1 final minus plus m2 v2 final. There we go. Yeah. Whoa! What's up? So yeah, and if you had three objects, you would go up plus m3 v3 initial. If you had four objects, it'd be plus m4 v4 initial. If you got 5 objects, you go further. If you get 10, you go, screw that, I'm using a computer. Because it's too much now. But you could, yeah, you could have, all kinds of. I can't remember. There is one problem I'm going to assign you where there's 4. But it's fun. It's fun. It's fun. It's got fireworks.
4.
That's 4 too many.
But I don't think I'm assigning it until next week. Now, a bit of notation here. You're free to use this. This is fine. This is totally legit to use this. However you want, you think works best, you go for it. You do you. Attendance gets a little crowded over here after a while, right? You start writing sentences in the subscripts. Because we got 2 objects and initial moments and final moments. Often, the assumption of the convention here that physicists use is that whatever the initial thing is, if it's blank, that means it's initial. So m1 v1, m2 v2, that's the initial moment then. And then instead of notating that final there, to get rid of those subscripts, yeah, we use a prime notation. Why? Because we want to confuse you. So yeah, that tends to be the notation that's used. Now you always start with this. This is the law. That's the physics law right there. Again, don't break the law. Yeah, you always start with the law, and then you can go to the momentums of your object and solve the problem. But you always want to start with the physics law, just like starting with F net equals ma. If you're using impulse momentum, you're starting with impulse equals change in momentum, etc., etc. Using work energy, the work done is equal to the change in energy. Those are the physics laws. Questions here so far? Comments, concerns? All right. So yeah, depending on the way you look at it. All right. Let's see. I'm going to start here. Yeah. This was your lab. I know it's been a while.
Oh, 3 of the.
Yeah, I'm starting with collision 2, which was again that same.
What's that lab?
It's like where you push it.
So starting with collision 2, which is this one, right? At the end, both carts are moving this way. It's just you can see some of the momentum of this cart was transferred to this cart, right? At first, this one's moving fast. It transfers some of this momentum over to that one, but it's still moving as well. It's still got some momentum. Correct. Not perfectly elastic, but not. Okay. So again, if I call the whole thing my system, the momentum, the total momentum, this is exactly what you just kind of saw. So you got, then I could, so starting with the sum of the momentums at the beginning equals the sum of the momentums at the end, you got m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. Right there, and you can go and solve them. Often with these things, you're solving for what's the velocity, the final velocity of the object. What was the initial velocity of this object? We're going to do something involving like bullets. How do you find the velocity of a bullet? Using impulse and momentum. So yeah, a lot of cool fun things. And then go to solve. Okay. Before I go into the, and we call this type of collision an inelastic collision. And that is a collision where kinetic energy is not conserved. Oh, because yeah, was your kinetic energy conserved?
No.
And that I think in none of them, right? None of them it was it? Yeah. So yeah, and so all of the collisions that you guys did were inelastic collisions. The kinetic energy was lost. I'm going to show. I'm going to show. It's what I think is a cool video. It's more of a lecture. Of why that's the case. Why is the energy lost, but the momentum stays there in the on the scale? Yeah. To give you guys an example, and I think I showed this class already. Actually, I showed you guys the elastic collision.
I don't know.
I'm pretty sure I did.
I want to watch it again.
It is fun to watch. So here you go. Here's an example of an elastic collision. So let's do inelastic one more time. So inelastic collision, you get that moves. This is still moving, right? So here's an elastic collision.
Well, perfectly elastic is my favorite.
So perfectly elastic and elastic are pretty much the same thing. But here we go.
That is so satisfying. Oh!
So you can see, right? Momentum is completely given to this one now,
Get those balls.
right? And so yeah, you can see the momentum is completely given to the second one, right? And that means also then the total energy was given to this one, right? Because if this one's now moving at the speed that one was going, it now has all the kinetic energy. This one just basically gave all of its kinetic energy to
Energy
this
is
one.
not lost.
But that's not always the case. So kinetic energy is conserved here. But not always is that the case. So for example, if the mass was different,
That's dangerous.
It's like the Hanks.
I don't got matches.
Light
Smack it.
So, all right.
Thermal energy.
Yeah.
it. It'll eventually hit
Ball.
So, okay, here we go. What do you guys think's gonna?
Wait, can you do it with the magnetic balls? Or the steel? You know how you like hit them together?
No, there's not enough room for that.
Yeah.
All right, here we go.
There's not enough room for that.
What happened? What was different?
That one
It's
went back.
Yeah, it went back, right? It didn't stop. Well, it shouldn't have hit. If it hits, it's not gonna be. See, it went back the other way, right? That's in order to conserve that kinetic energy. Well, and momentum, right? So some of the momentum is transferred over here, and then this goes the opposite direction to basically conserve momentum because this thing now is pointing in that direction, and but also to conserve the energy now, right? If it has no other choice, it can't go, faster than this thing. right? If it's going in this direction, because if it does, it's going to go right through it or something like that, right? So if it needs to conserve the energy, if it needs to conserve the energy, it'll go back in the other direction in order to conserve that energy right there. Yeah. So cool. Yeah, let's go into the other. So there's elastic collision. Collision where kinetic energy is conserved. Pretty rare. Pretty rare in the macroscopic world. Car crashes, hitting people in the hallway, those are all inelastic collisions. You hear sound, you hear, even this technically is an inelastic collision, but it's a very good model of an elastic collision. So